No? Yeah, good. Can you hear me?
Hi, we can hear
Yeah,
you.
okay. Okay.
If you're talking to the left side, then it doesn't look like.
I'm going to talk to this side then. Sorry, you guys see the other side. Now you know you need to switch a little. But, or I can just stand here and then talk. So. Raise your hand or something. Mhm.
Careful, it's glass, yeah?
I'll give people 2 more minutes to find the place. Yeah, just come forward. For those of you, yeah, just keep coming forward. Got a lot more space in the front. Yeah. Yeah. Okay, good morning. It is morning, especially for some of us from US. So my name is Sharon Tu. I'm from University of Notre Dame. I'm the general chair of ESWEEK 2023, which is the 19th edition of ESWEEK. And just also want to point out that this is the first in-person ESWEEK since 2019. I know some of you are at 2019, but I think it deserves a nice applause for all of us to be here. And so today, what we're going to talk about, of course, is Embedded Systems Week. And I kind of just want to point out, embedded system is really having at a very critical moment. And the reason is we are actually seeing a confluence of machine learning, AI, cyber-physical side of interactions, and of course, lots of emerging computing platforms. All of these together is making embedded system the most complex as we have seen. And I think it's just going to become more complex. And that presents lots of challenges, lots of opportunities for us. And that's why we're all gathered here. And we're trying to, as a community, to think about how to deal with all these complexities. And because of complexities, the community is also a very broad, diverse community. And I'm not going to say every single spike here, but I'm sure you can, maybe each one of us will identify at least with one or two or even more. Okay? So because of that, we gather together here and we want to exchange new ideas. We want to share your most advanced development so far. And of course, networking and making new friends and meeting old friends. So if you are curious about where all the 19th has been, and this is thanks to Avril, I just add one more slide, one more picture on here, right? So we're here in Hamburg. And here's the attendance so far. The data is Friday, as of Friday. So maybe we'll have some more. I'm sure there's a little more positive trends since the Friday. But we are still, if you look at here, last one is 2019. Those numbers, of course, are really nice because lots of people are attending virtually. And so we are, kind of on par with some of the earlier ones, but not as good as one of the amazing ones in 2017. We were still talking about that one. And for some of you who are new, ESWEEK also has a very interesting publication model. We actually, especially for this year, we introduced a new publication, IEEE Embedded System Letters. So you can see we got 3 publications, ACM-TECS or TCAT. This year is ACM-TECS, ESWEEK Proceedings. And the reason we have that is we got 2 different tracks. We have the full paper track, we call it. And then on the other side, we have this late breaking track. And then, of course, we also have our regular work in progress and special session track. So those are the 3 different type of publications. The good news, you're here, is you can access all of these today, tomorrow, the whole this week by going to the attend at ESWEEK publications. You'll find all of them. So for now, I'm going to ask all the people who have contributed a lot to the 3 different conferences come up to discuss their programs. And the first one I'm going to call up Swaroop Punya from University of Florida, and he's going to talk about the cases conference.
Thank you, Sharon. Hopefully to be here today. And of course, I have been privileged to serve as program chair for cases. And I would like to acknowledge the great help I received from my co-program chair, Jana Dopa. Can you please raise your hand, Jana? Hey, thank you. He's from Washington State University. Okay, so we received some data here. We received 77 journal track submissions this year from 117 abstracts. In 2021, we received 100 submissions. Basically, this should be 2022. Basically, we went down a little bit. I have been told that this is primarily because of the target journal, but I see a significant rise from the year before. We had 44 submissions. So if you compare with that, definitely it's a big jump. And we hope that this trend will continue irrespective of the target journal. We will receive good number of submission in cases because of the focus of AI ML hardware in IoT and the convergence of AI with IoT and embedded systems. So we ought to see that, we would like to see that trend, and I am hopeful about that. We had a very strong TPC with 60 members, and of course, each of them worked really hard. We had 418 reviews with about 4.5 reviews on an average per paper. And from there, we selected 32 papers, and eventually we down selected. It was very hard, 21 papers for including into the cases program. Sharon mentioned we had WIP track and also late breaking track, and late breaking actually has got a lot of visibility because of the hard work of the publicity chairs. We received 7 submissions in work in progress, 10 in late breaking, and of course, some of them went into the program, as you can see here. One thing I would like to mention that we actually increased the number of countries from where we received the publication and the submissions. Last year, it was 17. We went up to 24, and as usual, United States, India, Germany, China are the largest contributors in that. We have a very strong program. We welcome everyone to attend those sessions. We have 7 sessions. Each session has 3 journal tech papers and few WIP and LB papers. And the ones in with a star mark next to it has a best paper candidate. So definitely we welcome you to attend that. These are the 3 best paper candidates for cases. Of course, congratulations to all of them. One of them would go into will be selected as a best paper by a very well crafted committee, best paper selection committee, who will attend these papers and select one. With that, I will hand over to the program chair from CODES ISSS. It's Muhammad Abdul Al Farouk from University of California, Irvine.
Thank you, Sharup. Good morning, everyone. I'm the program chair of CODES ISS, and program co-chair is Mohammad Shafiq. Unfortunately, he couldn't come in person, but I believe he joined over Zoom. To give you some statistics about the CODES ISS this year. So I took 3 years of data, 2021, 22, 23. So you see that paper numbers, as Sharup mentioned already, that number of papers varies depending on the target journal. So, but 2021 and 2023 are almost the same numbers. In fact, 114 and 117. This year we received 71 full submissions and abstract 114, and 17 papers are accepted with acceptance rate of 23.9, a little bit lower than previous years. And then we received 19 work in progress and 9 papers are accepted. And this year, Sharon and Sharup mentioned that we have started these late breaking papers, that 4-page papers. This was very popular, by the way, and very good quality papers we received this year. And we accepted 7 papers out of 10. So this is the first time, and the quality was so good that we decided to accept more papers from the late breaking session. And the number of papers, it has been historically from very diverse all over the world. We receive papers, all continents covered. We see, you see the acceptance rate. The orange is the number of papers submitted, and the blue one states how many papers are accepted from each country. We have also a very, for 17 papers with the work in progress and the late breaking. So we combine all these 3 types of papers and form these 6 sessions. 6 sessions, and you'll see that traditional CODES ISS topics, memory model, but a lot of emphasis on accelerated design. And we have also, we have seen the chiplets and other topics are also coming, and security and reliability. So we covered a very, robust topics that within the CODES ISS area. And with the star, so today you will find all the 3 best paper candidates will be presented in the next 2 sessions. So by noon, basically all the 3 papers will be in the presentation. So I welcome you all to attend those, of course, other conference tracks and also, but these 3 papers definitely. So the 3 papers for the committee that decided to select, and we considered multiple criteria. Definitely we got feedback from the TPC committee, and then we have again had a second review by the TPC chairs, and then also other criteria and different criteria. And we selected these 3 papers based on also the topic and many other things. So you'll see that AI accelerated design. Second paper is on chiplets. The third paper is very classical embedded systems on intermittent deep inference topic. And all 3 papers are exciting. And then we have also formed best paper selection committee. And the best paper selection committee has also decided their own rubrics, how the decision will be, and they will be listening. And others, they will also probably solicit some suggestion from the other people, and then we'll know it on Wednesday. With that, I will conclude and invite Claire from Andrea, France, to present about EMSoft.
Thank you, Mohamed. So it's my pleasure also to be here today for the third conference of the Embedded Week 2023. So it's the 22nd International Conference on Embedded System Software. And this year, as was greatly helped with my co-chair, Alessandro Biondi, who will be here next year. So this year, we received 129 abstracts and 90 papers. So compared to the previous year, it's a little bit less. So I hope it's only an outlier, that next year it will go back to the regular number of submission. So we had 49 PC members from all around the world. These members come from also different genders as much as we could, senior and junior. We had a two day of PC meeting to decide among the 90 papers which go to the next round. So among the 90 papers, 29 went to the second round, and finally 29 to the second round and 21 to the final round. So if you look at the country, again, it's from all around the world, Europe, Asia, and America. So for work in progress, we did not receive much, but that's usual for EMSoft. So 10 submission. And for the LB, we received 8, but only 3 accepted. So we were a little bit rushed, maybe hard, who knows. So for the sessions, so I made a mistake because I follow the cases agenda, which is not mine. So for Monday, we have 3 sessions from EMSoft 1 to EMSoft 3. The Tuesday, we have 2 sessions, and Wednesday, 2 sessions. So you shift by 1 from Tuesday and Wednesday. So when there are stars, it means that we will have some best paper candidate. So we selected the 3 best paper candidates. So as explained by Mohamed, we follow exactly the same approach. So we received some nomination from the PC members. Us as TPC chair, we review also the paper. And finally, we got 3 papers. So 2 on synchronous languages and 1 on memory. So go to the first 2 sessions of EMSoft and you will have a chance to watch them. Thank you very much. And I go back to Sharon.
Great. So you can see that we have 3 amazing conferences. The TPC chairs and the TPC members have worked really hard. Let's give them another round of applause to thank for their hard work. Besides the 3 conferences, ESWEEK has also a bunch of other programs that make it really a rich experience. Unfortunately, if you just arrived and you haven't joined, some of them already passed. So here are some examples, other programs that have happened on Thursday and Friday last week. This is the education class. This is the 2nd year we're doing this, and Avril is the one that spearheaded this effort. And the idea here is we invite very established educators to present topics on some very big topics relevant to embedded systems, but also more on the basic side. So there's actually lots of attendees from worldwide, and they're very well accepted. And besides that, we also had yesterday, we had 5 tutorials. 2 of them are long ones. They are given by industry, and there's 3 short ones. Again, if you missed it, make sure next year you come early so you can join the tutorials. We also had the really very first, our diversity event yesterday, and we have some invited presentation. We have 2 panel discussions, and so it's a first attempt. We would like to see more people to attend, so look out for it next year. Now, for the rest of the week, we're going to have 3 inspiring keynotes, and first keynote is going to be given by Dr. Sharita Advi from University of Illinois at Urbana-Champaign. And she will be giving a talk talking about the era of immersive computing, especially from the embedded system side. And on Tuesday, we'll have a keynote given by Heike Riel from IBM Research, and she will be talking about quantum computing. So it's again a little bit away from us, but we'll see how, as embedded system people, how we can contribute. And also the on Wednesday, the keynote was going to be given by Lotte Thiele and from ETH Zurich. It just so happened I realized both of them are from Zurich, but they are totally different. So Lotte will talk about resilient embedded system, the era of machine learning. Now, we also have 4 special sessions. I list some of them. I'm not going to go over them. Professor Sri Paramaswaran is the special session chair. So he helped put together 4 excellent special sessions, and they're going to be on Monday, Tuesday, and Wednesday. So that. Now we also have the theme, this special theme for this year is we make it into Global Semiconductor Renaissance. What do we mean by that? You're going to hear more at the 2 panels that Professor Marilyn Wolf has put together. And the key is trying to think about all these European had CHIPS Act, US had CHIPS Act, all over the world, Korea, everywhere. There's lots of enthusiasm on semiconductor industry. What does it mean to embedded system design? What are the new opportunities, new challenges it's going to bring us? So these 2 panels, one is more focusing on industry, the other panel is focusing more on education. We really want to discuss these topics. So make sure you join them. Oh, I should have showed the other panel. So one panel is on Tuesday, the other panel is on Wednesday. Okay. And we also introduced several new competitions. The first one is called Tiny and Fair Machine Learning Design Contest, and it's chaired by Weiwen Jiang. Unfortunately, he couldn't make it because of visa problem. And you can see the numbers there. It's really very well accepted. 72 teams participated, and teams can repeatedly submit their entries. So that's why you see over 700 submissions. So they can keep improving. So basically the problem was given early in the year and they keep improving until I think a week or 2, several weeks before the conference, they close it. Then they look at the different metrics they have set up, they pick the winners. And there's actually 2 tracks. One is on segmentation and the other one is classification. So you're welcome to join them for the presentation after the keynotes. I showed the time there. And we also introduced a new embedded system software competition. This is spearheaded by Ganapati Bhatt and Biraj Roda. And they actually come up with this really brilliant idea thinking about there are lots of tools in embedded systems. How about recognizing them? How about let the community know what are these tools out there and how can they benefit the whole community? How can they broaden their impact? So that's the idea of putting together this embedded system software competition. And for the very first year, with a very short time, I was really amazed that they actually got 9 teams to present their tools. So you can see the times when they're going to present. And there'll also be a demo on Tuesday between 5 and 6 o'clock, and they will choose the winners. So come and join them and see what are all the exciting things going on there. The third one is ACM Student Research Competition. This has been going on for a while. This is organized by ACM SIGBED, and it's chaired by Wan Li Chang. And this one is actually different SIGs have different these competitions. Within the competition, you pick the winner, and then the winner will actually go to the ACM level competition, and the grand winner actually will get a chance to participate in the Turing Award ceremony. So it's really exciting time for a lot of graduate students and undergrad students. So make sure you find the time to stop by to look at those programs. We also have a PhD forum, just like what we had before, that's chaired by Shelley Lin. And the presentation going to be, again, this evening. I think it's after 5 o'clock. This year, we also put in a recruiting event. We want to give our industry sponsors access to our students, also give our students an opportunity to meet with the industry representatives. So this recruiting event is chaired by Jeff Zhang. And we have 7 companies going to join. And before the conference, we ask the students to submit their CVs, and the companies will have their desks. They talk to these students. So if you're still a student, you say, oh, I haven't submitted my CV yet. It's probably okay. You still go stop by their desk and talk to the representative to find out what they want and how you can prepare yourself better in order to, understand how the industry works. I think that's a great opportunity. Again, later this evening. We also going to have 2 symposia, that's Thursday and Friday. One is memo code, and this is the second time I think they're with us. And then there's also Knox, which has been with us for a few years. And I'm not going to pronounce all these names one by one. Okay, then on Thursday, we also have several workshops, and Professor Robert Dick is the workshop chair. He has put together 3 wonderful workshops, and their topics are quite varied, right? One is on compilers, toolings for edge AI, and the other is more for tools for processing in memory. And the third one is international workshop or rapid system prototyping. The last one has been with ESWEEK for a while, but the first 2 are relatively new. So it'll be great to stay and interact. I think the workshop has even more intimate feeling, so you get to really talk with the presenters and discuss among the colleagues. So it'll be a great experience. We're going to have 2 award ceremonies. So tomorrow, we're going to give out the Test of Time Awards. And we actually, each of the winners will get the chance to give a little short speech. So it'll be very fun to hear all these visionaries. When they published paper in 2007, 2008, how does those papers really still impacting our work today? And then on Wednesday, we're going to present lots of other awards, of course, especially the best paper awards from the 3 conferences you have heard, and lots of other awards. So make sure that you get up early, still 8:30, to attend these. And with that, I think I'm going to call Heiko, our local chair, up to tell you more about the logistics. And if we are here enjoying all this, it's all because Heiko and his team's effort. So first of all, before he starts, let's give them a round of applause.
Thank you so much. As Sharon just said, it's a team effort. So thanks also to all my team members. You recognize them with the white t-shirts. So this year we are on campus of TUHH, and ESWEEK takes place in 2 different buildings, 2 different locations. You successfully managed to find the H building. Congrats. The other activities take place around about 100 meters away in the A building, so it's 3-4 minutes of walk. We have indicated the way with signs, so I hope that nobody of you gets lost. What's going on in these buildings? No, the other way, like that. In this building where we are currently, all our plenary sessions will take place. In the other lecture hall, AMSOFT basically will take place, and the Knox Symposium. We have, of course, critical coffee area over here and some rooms indicated in red for networking and talking and so on and so forth. You already found the registration desk, I guess. So that's basically what's going on in this building. No, I forgot this room. This is where CODES and ISCube will happen. And in the A building, we have the room over here with the number 13. This is where cases will be run, and critical also, the area indicated in green, this is our central lunch area. So there we reconvene in order to have our lunch, and we also have distributed coffee corners here and there. So that's it for the moment. Enjoy your time at TUHH. Welcome to Hamburg.
So of course, like Heiko said, this is really a great team effort. And I just want to acknowledge everybody who have contributed to organizing the conference, as well as picking the papers and doing all sorts of work. So I don't have time, of course, not pronounce every single name, but if you see them around, if you recognize them, do thank for their great effort here. And also we have our steering committee and sponsor representatives give us a lot of guidance and tell us what is a historical way of running ESWEEK. So I also very much appreciate their help. And of course, last but not least, we have lots of industry sponsors. I also want to acknowledge their generous support. And of course, as our sponsoring societies. So now let's move on to our official program. Our Mondays start with a keynote. And the keynote going to be given by Professor Sarita Advi from University of Illinois, Urbana-Champaign. Let me just say a little bit more about Professor Sarita Advi. Professor Advi is the Richard Chung Professor of Computer Science at University of Illinois at Champaign, where she directs the Immerse Lab, which is the Center for Immersive Computing. Her research interest spans the whole system stack, ranging from hardware to applications. And her work is particularly on data race-free Java and C++ memory models from the foundation for memory models used in most hardware and software systems today. Her reality system and research testbed, her group actually released the Elixir, that's the Illinois Extended Reality Testbed. And it's an open source extended reality system and research testbed. And the launching is actually hope to democratize the XR research, development, and benchmarking. And that really has made a big impact in the community. And she's also known for her work on heterogeneous systems, software-driven approaches for hardware resiliency, etc. She has received numerous awards. I just list a few of them here. She is a recipient of ICM IEEE CS Ken Kennedy Award, and she's a fellow of ACM and fellow at IEEE. She is also a member of the American Academy of Arts and Sciences. And there's more and more awards. I think I'll stand here and take another 5 minutes to say all the other awards. So with that, let's just welcome Professor Advi to this podium.
Hello, can you hear me? Yeah, great. Thank you so much, Sharon, for that kind introduction and also for inviting me for this event. Really blown away by the number of events that you have here. Looks like a huge organizational effort. So I look forward to the next few days. Okay, so the title of my talk is Enabling the Era of Immersive Computing, a Rich Agenda for... okay, I should grab my talk. Yes, no worries.
It looks too real.
Let's see, I don't understand German yet. Here we go. All right. No worries. Okay, so the title is Enabling the Era of Immersive Computing, a Rich Agenda for Embedded Systems Research. And here you see several videos that reflect the research of many of my colleagues, including using AI neural models for content creation for immersive systems and open source immersive system testbed, surgeons using immersive technologies for pre-surgery planning, and a robotic telepresence system. So today I'm going to divide my talk into 3 pieces. The first is about Immerse, which is the Center for Immersive Computing. That's a campus-wide center that I direct, and many of the videos that you saw on the title slide come from my colleagues there. The second part will be about Elixir, which is the Illinois Extended Reality Testbed that came from my group. I'll talk about that. And finally, I will talk about research that is being done by us and others using Elixir. Okay, so let's get started with a brief introduction. What do I mean by immersive computing? Immersive computing is, to me, the seamless integration of the virtual with the physical. And so in this picture here, you're seeing, just imagine yourself interacting with the hologram of your colleague that you're working with and interacting in your own physical space, your own physical environment with a bunch of physical and virtual objects seamlessly. And by seamlessly, we mean you're comfortable, you're mobile, you can do this all day, and you have rich photorealistic experiences. So with this, we include things like virtual reality, augmented reality, mixed reality. Collectively, these are known as extended reality or XR. I will be using the term XR interchangeably with immersive computing in this talk. And also includes metaverse, digital twin, spatial computing, and all of the other buzzwords out there. I read about the Appleverse. I hadn't seen that before, so that's included too. So I would that, not just me, many people believe that immersive computing is really going to be a transformative technology. And this is going to transform and is already transforming most industries and most human activities, including healthcare, education, science, industrial design, manufacturing and maintenance, retail, entertainment, and so on. So we started, these technologies, if you trace back, I think the popularity really came from a lot of science fiction and entertainment and movies. But now we've gone to real world use cases that are helping a lot of people. So for example, virtual reality being used to help us autistic children navigate the world. These technologies were used to deal with COVID isolation for senior citizens, dealing with chronic pain, industrial maintenance and design, emergency management, crisis situations, and then a lot of use cases in the medical industry, both outside of the operating room. So for surgery planning, etc., our colleagues tell us that once they've used 3D immersive systems for planning out their surgeries, it's just a complete game changer for them. And then also increasing use in the operating room. So this is truly a new era of computing. Now, if we look at the previous eras, right, we had the mainframe era, we have the personal computing era where computers came in the home, the web and the cloud, mobile computing, and then now immersive. These were all transformative, right? They really changed how we designed, programmed, and used computers. And I believe the same is going to happen with immersive computing. And it's not just that they changed how we use computers, they really brought up new industries and new markets that we didn't have before. So, who would have thought about YouTube, right? Before the mobile smartphone came into existence and before the web and the cloud, right? Who would have thought about Airbnb and Uber and so on? And I believe the same is going to happen with immersive technologies. But we are not there yet. Lots of challenges remain, lots of opportunities. And this community is really at the center of a lot that needs to be done. And I hope to see a lot more work coming out from this community in this area. Okay, so let's focus on the technologies themselves. I said we want comfortable, mobile, all-day, rich experiences. Well, this virtual reality headset, which is what you're seeing in this picture here, is sort of what we kind of have got to associate now with these technologies. And for sure, if you've worn one, comfortable it's not, right? What you really want, if you want to wear these glasses, you want this form factor, right, which is about tens of grams. But the headsets that we have today are very bulky for the most part. About 500 grams is some of the best ones. The second thing about mobile and all-day wear, well, what that means is you want really a long battery life. You want low power consumption. You don't want your headset to burn you up on your nose. And so based on that, the desired power budget for compute is about 100 to 200 milliwatts. And what we have today in most of our headsets, or the best ones, is about 7 watts. And so, a lot of the recent Apple announcement, Meta, etc., a lot of those headsets, the battery life is about 2 hours. And in some cases, you have to walk around with a battery pack to get that 2 hours. For rich experiences, rich photorealistic experiences, you want high resolution, you want high field of view. And again, we have a huge gap between what is desired. So say 200 megapixels desired for high resolution, rich photorealistic experiences, but today's systems, we get about 7, okay? Bandwidth, right? If you want to be mobile, again, there's an order of magnitude difference. Collaboration, the big promise of these technologies is from collaborative experiences. We want to be able to collaborate between hundreds to thousands and more people, and we are not quite there yet. Finally, it's not just these features, but the constraints on the system in this area are very high. So one example of a goodness measure for such systems is the head motion to display latency. So I'm looking here, let's say, and now I look there. Well, my perspective changes, and what needs to be displayed before me needs to change. And for virtual reality, we want that time for the user to be comfortable, okay, so that you don't have cyber sickness, etc. We want that motion to what's known as motion to photon latency, motion to display latency, or motion to photon latency to be within about 20 milliseconds. And for AR or augmented reality, we want that to be about 5 milliseconds. So these are really stringent constraints within which you have to do all of what I just described. And there are many more technology challenges. I haven't even talked about the whole space of trust, security, privacy, etc. So one thing that's clear is that to deliver on this promise, there's no one silver bullet. We really need to bring together a whole host of areas: hardware, programming systems, runtimes, networks, distributed systems, security and privacy, graphics, vision, AI, sensors, displays, optics, audio, haptics, olfactory systems, and what have you. So this is the challenge, and yet the excitement of this area. When we started working in this area, this is one of the things that was really exciting, that we need to bring all of these systems or fields together. So that was about technologies. The next thing I want to talk briefly about are applications. So today, I showed you a few applications, right? And things are really moving on, but a big problem with immersive applications today is getting the content up and running. And so on our campus, for example, we have people working across campus, building immersive applications in many different areas. So in healthcare, in education, arts, industrial design, games, advertising, architecture, robotic telepresence, simulation, and much more. But one of the things that they will all tell you is that creating the content, bringing these applications up, and maintaining them is really challenging. Deploying them in a scalable way, so we have many people teaching using immersive content. Deploying this across large classes in a scalable way is still very hard. And of course, we still have all of those technology barriers that I talked about before. Assessment of these systems is also very hard. The goodness measures are not there. I'll talk more about that on the next slide. And so when we talk about enabling new applications in new markets, we still have major obstacles, even aside from the technology. So that's another challenge, but also an opportunity area. And then finally, more than anything else, this area really relies on the human experience. The metrics of goodness are tied so closely to the human-centered experience. And so if we want to evaluate these technologies and these applications, we need to be able to measure how humans respond to them and use those. First, we need to understand how humans respond to these technologies. Then we need to measure and then feed those measurements back to improve the system. The other aspect is that these are multimodal experiences. So it's visual, it's auditory, it's haptic, olfactory, etc. And lots of fields come into play again. So there's perception, neuroscience, psychology, design, usability, ergonomics. How do people collaborate? There's, we have people from educational psychology working on these issues. And how do we create the future spaces? What is the future industry floor going to look like? What is the future classroom going to look like, etc. when you have these technologies? And then finally, trust, which is again a very human-centric thing. So recognizing the need to bring all of these elements together, and that's the way we are really going to make big leaps in this area, we've put together Immerse, which is the Center of Immersive Computing at the University of Illinois. It has 3 thrusts: technologies, applications, and human experience. And here you see, let's see. Here you see a list of various colleges. So these are not departments. These are larger campus units that are part of Immerse. So, you know, as you expect, engineering and liberal arts and science, but also our College of Medicine, Applied Health Science, Education and Education Psychology, Fine Arts, Business, etc. We have members from all of these places coming together and trying to move this field forward. We do research, education, as well as infrastructure activities within this center. And I don't have too much time today to talk about the work that we are doing. The work that we are doing, but just to give you highlights of, you know, the sorts of large-scale problems that we are addressing here. So within technologies, there's a big focus on scalable system co-design. I'm going to talk a lot about this today in the rest of my talk. There's a big focus, as you might imagine, is on how do we use AI to rethink immersive systems? Today, you know, pretty much all aspects of immersive systems are starting to use AI techniques, and how does that affect how we think about these systems? What is the science of system design? When you have all these human experience-centric things, how do you actually think about designing these systems? On the application side, because of the big strengths that we have in these areas on our campus, we are focusing a lot on healthcare-related applications as well as education-related applications. We have a lot more, but this is our focus. We're building real test beds, end-to-end test beds, and based on these applications, so they provide us with experimental infrastructure to do the rest of the work in the center. And we are focusing, and we have a lot of work on building that application ecosystem that I talked about to get content up and running quickly and scalably. And then finally, in the human experience side, we have work going on in the experiential factors. How do we experience these technologies? Contextual factors. So for something like healthcare, there's all sorts of things related to FDA regulation, et cetera. How do we deal with them? So in the context of the applications. And finally, societal factors. So many issues related to these technologies, right, that are, you know, that are going to affect how we operate as a society. So all of this is part of Immerse. And hopefully I get to give another talk just on Immerse. But today we're going to move on and focus on the technologies part. Okay, so a common theme here is going to be something that this community really recognizes very well and has been doing for a very long time. And that is thinking across the system stack, thinking about co-designing different parts of the stack. Right, and with the end of Moore's law and Dennard scaling, of course, this is very, very crucial today. So I'm talking about from semiconductor technologies, hardware architecture, programming languages and compilers, systems runtimes, and algorithms and applications. And for this particular domain, it's not just that one single chip or one single unit that we are worried about. We are going to be looking at applications where there are going to be a lot of people interacting with each other, many different XR headsets, wearables, and what have you, connected to the edge, connected to the cloud with a network. So it's this co-design of this entire platform that really needs to come to bear for us to make leaps in this area. And I will talk a little bit, mention concrete things in all of this. And then it's not just, again, the co-design of these systems, but again, just to remind you, it's the human-centric experience. It's the visuals, it's the audio, it's the haptics, all of that. How do you measure the goodness of these things, and how do you co-design these systems driven by these human perception related goodness metrics? And really, this is this technology actually has the potential to do physical harm, right? If you don't design your system well, the user can get dizzy, the user can get headaches, the user can throw up, right? How do you deal with that? How do you measure that? And how do you design systems so that this does not happen? So again, human perception driven force system enabling new applications. So we were really excited when a few years ago, we realized, okay, this XR is happening. This is what I want to work on. You know, Moore's law is dying. Dennard scaling is dead. I want to design systems for this area. Very excited. Saw all of the opportunities, right? I mean, how often do you get to work on things where there's an orders of magnitude opportunity across so many dimensions? But we came to a total halt very soon after we started working in this area. Why? Because there were no benchmarks, no reference systems, no open source, anything for us to work with. How do you design these systems if you don't even, a lot of the end-to-end view of the system that I'm proposing here was actually behind firewalls in companies. There was just literally nothing available for us to get started from. So we realized that really to make an impact in this area, the first thing we need to do is address this very large barrier to entry for open R&D for systems people, right? Of course, there are, you know, graphics people working on these algorithms, et cetera. But if you want to do this end-to-end expansive view, there was just literally nothing. And so we pivoted and we said, well, that's what we're going to do. We are going to first build a testbed to democratize work in this area, and then we're going to use that to do the research. So what actually started off as a really small project, you know, you're supposed to get, we got seed funding for $50,000 from a center I was part of. We thought in 6 months we'll write a benchmark, but it became sort of my whole life for many years. And a lot of people, a lot of students and industry partners joined us. So we had huge support from NVIDIA, Meta, ARM, et cetera, from the beginning to get this system up and running, and now Intel, Cisco, et cetera. And a huge number of consultations. And I want to recognize all of these people from academia as well as various companies. So this is how Elixir, which stands for Illinois Extended Reality Testbed, was born. So it is an open source full system XR testbed. It has state-of-the-art XR components with a modular runtime. It's compatible with OpenXR, which almost congruently emerged as a standard, as an open standard for the interface between XR applications and the XR runtime. And we formed a community consortium. So Elixir is a community testbed. Again, the goal is to democratize R&D in this area and benchmarking data sets, et cetera. You know, this is, we maintain a very active, robust open source infrastructure and community. And it's been used extensively to characterize XR systems and used for research. I encourage you to go visit elixir.org. In fact, today we, in honor of ESWEEK, we have a new release coming out with a lot of new features. So I encourage you to go ahead and give this a test drive. Okay, so before I go into details of what Elixir is, I want to just show you some videos, some demos that show that this is real, right? So this is not just vaporware, this is a real system. And here you will see how we use Elixir on a day-to-day basis. Okay, in the next demo, we'll show you in a more production sort of basis. So you will see the, let's see. Here we go. Okay, so here, this is my student walking around in our lab. There are no headsets yet. He's walking around in a lab with a camera. Okay, so this is a physical space he's traversing. This is the third-party view of where the headset would be as he's traversing in this virtual space. Okay, so this is the Elixir virtual room. And then this is what you would see through a headset. And here we're just seeing it on our monitor with a debug window telling us what's going on. So this is how we use Elixir on a day-to-day basis. You don't need a fancy headset or anything like that to actually use it. And then here we have Elixir running on this PC. very fancy novel contraption here that my student Jeffrey is rolling around. So it's a full software stack. And then it's sending, the PC is sending pixels to this headset, and Joseph here is having this experience. So this is what Joseph is seeing. This is a common application called Sponza. It's running on a game engine. He's walking through a castle, and you can see that this is rendering really well. It's tracking really well. So this is a real system. Okay, so now, of course, here Jeffrey had to walk behind Joseph, but then we put Elixir on a backpack PC, and so now Joseph can walk around independently with this backpack PC and enjoy his experience without worrying about having someone else. So again, the headset is being used purely as a display. All of the other software stack is running on Elixir, and what you have now is a completely open source end-to-end software stack for XR that you can measure, profile. You can change, do whatever you like with it to change the experience. Okay. So here are more details. This is how it's sort of a generic XR system looks like. So we have three main aspects. One is the perception pipeline. I'll tell you more about each of these in a bit. The other is the visual pipeline, and then you have the audio pipeline, and then you might have haptics and so on as well. And all of these communicate through a communication interface and runtime. You run an application, an XR application on top of all this. For, as I said before, we can run OpenXR applications. We use the OpenXR implementation from the Monado group to interface with the Elixir runtime. And all of this is running on a mobile device. Right now, actually, when this slide was made, I should say, this was all running in software on an embedded system like we run on NVIDIA Jetson, etc. But the whole point of this exercise is to figure out how to build hardware, faster hardware for all of this. And so you will see some results for that in today's talk, but that's all ongoing work is what parts do you really need to accelerate, etc. And then since we started, we also now have the ability to offload some of these components to a remote server or the cloud, etc. And I'll talk about that in a bit as well. And the reason to offload, of course, is to save power, have more compute resources available, etc. Okay. So let's go over each of these subsystems one by one so we get a sense of what these systems need to do before I go on to telling you what we've done with Elixir. All right, the first part is the perception pipeline. And this tells the system where in the world the user is and what does the world around the user actually look like. Okay, so it involves sensors like cameras, IMUs or inertial measurement units, etc. A key part of the perception pipeline that you will see in the rest of this talk over and over is the head tracking. So figuring out where the user's head is, okay, as the user is moving around. And there are various ways to do this. One of the most popular ways is through what's known as visual inertial odometry, which uses the camera and IMU sensors. So this provides a 6 degrees of freedom, position, and head orientation, or what's known as the pose. The VIO part, the visual inertial odometry, is a very complex piece of computer vision related software or hardware for that matter. And it provides good, accurate poses, but it takes a long time. Okay. And since the user is moving, pretty quickly, and we talked about that motion to photon latency, we need poses at a faster frequency as well. And so we resort to the IMU, which gives you faster poses, but they're less accurate. The IMU integrator takes both of these pieces of information, the IMU's inaccurate fast poses, the VIO's accurate slow poses, and provides high frequency accurate pose estimates. There's also a need for a pose predictor that looks into the future and predicts where the user is going to be looking in the future so that I can predict what perspective we have to actually project for the future frame that I'm going to display. Scene reconstruction uses RGB depth cameras to build the dense 3D map of the world that's around the user so that we can then manipulate and interact with our physical world. We have eye tracking, which tracks where the user's gaze is. Eye tracking is not completely integrated into Elixir in the sense that we still use data sets. We don't have a good eye tracking camera yet. So we're still using data sets for this. For the visual pipeline, this is again the pixels that Elixir is going to put out. So it takes information from the perception and then figures out what pixels to display. A key aspect of the visual pipeline that you will see later is called asynchronous reprojection. And the idea here is that, as I mentioned earlier, when I am from the point that the user moves to the point that we actually display the image, there's a lag, right? And so asynchronous reprojection, it takes the frames that the rendering engine submits to the system and says, this rendering engine assumed the pose or where the user was going to look, it got that information from a while ago, and that's where the pose was predicted to be. But really right now the pose is something else. And in fact, by the time the frame is displayed, is going to be something else. And so it quickly warps the frame so that it can be projected using the updated pose. Okay. And this is super critical because this is what cuts down the motion to photon latency, because now we are predicting the poses and quickly warping the frame so that we have a very low latency gap here. Okay, so this is fast but very critical. And then there's lots of distortions and corrections we have to do due to lens due to the headset lens characteristics, etc. We do all of that. There's a computational holography component. We don't have holographic displays, but we have the computation to do this so that we can provide multifocal planes, etc. These are well-known problems and solutions in XR, and Elixir provides support for doing research in all of this. And then there's the audio pipeline where there's audio encoding, where you encode multiple sound sources into high order ambisonics sound fields so that you get that 3D effect of the sound. You can play back, you can rotate and zoom this HOA sound field based on where the user's current pose is. So if I'm looking this way, you get the 3D effect of where the sound is coming based on where you're looking. This requires performing something called binauralization that accounts for the shape of the user's ear, head, nose, so that you can model of the reflections of the sound and so on. So you get a realistic, rich system. Okay, so those are the different components, really quick walkthrough so we get a sense of what the system is. But XR is not just a collection of components. You saw earlier, this is a full system, right? And so it's really, you're sort of doing a disservice if you're thinking about this as these individual isolated components. So here is a typical XR system data flow. There's the IMU, as I said, which works at a really high frequency. There's the camera, which works at a lower frequency, and VIO takes information from both the IMU and the camera. There's the IMU integrator that takes information from the VIO and the IMU. And then there's eye tracking, there's 3D reconstruction, which takes information from the camera. There's the application that's actually, doing the rendering and the simulation, all of that stuff, whatever the application wants to do, gets information from the eye tracker, from the IMU integrator, from the reconstruction, etc. There's reprojection that's getting information from all of these other places, the hologram, the audio encoding, playback, etc., etc. Okay, so all of these things are all interacting with each other. And you see dashed and solid lines there. The solid lines means that the dependencies are really hard dependencies. The dashed line means that if the producer is not done by the time the consumer starts, it's okay. The consumer can take something that's a little bit older. So they are asynchronous dependencies. So you have different components here working at different frequencies. There are multiple interacting pipelines. These are synchronous and asynchronous dependencies, multiple quality of experience metrics, lots and lots of stuff going on. And Elixir models all of this, or not models, it actually executes all of this. So, so there's correctness, right? We do all of this, but one thing that we, really were very, very careful about from the get-go is to make the architecture of Elixir be very modular and flexible. So all of the Elixir components that you see here, like the reconstruction, eye tracking, etc., these are all plugins. They can be separately compiled. You can develop them independently. They're dynamically loaded, and you can very easily swap and add new components, new implementations. Pretty much for everything here, we have different implementations, and you can just swap them in and out. So it's very modular and flexible. At the same time, we ensured that we were efficient. And so, so the flexibility does not come at the cost of efficiency. And the reason is that we are using a fairly standard event stream based system for publish and subscribe. So the producers and the consumers publish and subscribe their information. But we maintain the idea of synchronous and asynchronous consumers. And we do all of this in a copy-free shared memory mode. So very lightweight implementation. Okay, so again, the entire end-to-end system balances flexibility with efficiency, and this has been a huge tenet throughout. Okay, so what kind of applications do we run on top of this? So this is the runtime, what's running on the headset, but then you want to run the applications. We can write applications directly to Elixir using Elixir's native interface. But the really cool part is that now that we have OpenXR, which, as I mentioned earlier, is a new standard, so that all the application vendors can write their applications to this new standard for any runtime. We support OpenXR through the Monado Group's OpenXR implementation. And because of that, we can now support commercial game engines like Godot, Unreal, for example. So you write an application for Unreal and you can run it on Elixir. And in fact, today's release has so this is new. So today's release has support for this. Okay. In addition, we have a lot of telemetry. Lots of end-to-end quality metrics that you can measure. Just a few here, motion to photon latency, metrics for image quality. We have more state-of-the-art metrics now. And again, lots of sort of standard telemetry like frame rates, missed frames, how long did something take, power. We have a very extensive logging infrastructure that's also part of today's release. It's a very nice comprehensive infrastructure. Okay, so that was about Elixir, and so now the question is, what did we do with this, right? What are the findings? Okay, so to the first part, I'm going to talk about just a characterization, all right? Because this was not understood as well when we started this work. There was a lot of sort of company numbers, but there was no like academic published literature. So to do this evaluation, we put together a basic XR system. And one of the things you will see is that there are so many parameters that go into this XR system that you really need a well-tuned system before you can actually start doing measurements. And so we spent a bunch of time tuning the system so that we picked the right frequency for the IMU, the right frequency for the camera, etc. We did all this manually. And in fact, one of the big research topics for us is how do you automate this? And we have a paper on that, but still lots of work to be done on the automation. Okay, so we studied the performance of this configuration on a high-end desktop machine. Now you're not going to run XR on a high-end desktop machine unless it's tethered to the headset. But this gives us sort of a high watermark as to what is possible with today's technologies, right? What can I actually run? And then we also ran on embedded NVIDIA Jetson class machines. This tells us, what is more realistic for today's XR systems. We ran a bunch of applications on the Godot game engine. I don't have the time to go through all of the results here, but just to give you a basic summary, we looked at frame rates for all of these applications on all of the systems we measured. the execution time and distribution, where was the time going, and which component, VIO, rendering, etc. And then the power, right? How is the power distributed across which components? Was it in the DRAM? Was it in the CPU, and so on? What is the quality of experience like? What is the motion to photon latency, et cetera, et cetera. So we did all of this analysis, right? These are the first published performance, power, and quality of experience results for end-to-end XR systems. And what I will spend a little bit of time on is the implications of all of these results. Okay, so the high-level summaries and the implications, and then the next part will be telling us what did we do with these implications, right? What was the research that we are doing? Okay, so the first set of implications are from the end-to-end system measurements, and the first thing we confirmed is yes, there is a huge performance, power, and quality of experience gap between current systems and what we desire, right? So we sort of knew this going in, but it was nice to get a quantitative confirmation. And this leads us knowing where Moore's law is going or not going, and Dennard scaling, not going for sure. We need to specialize hardware, software, and entire system, because just waiting for transistors to get better is not going to cut it. The other interesting thing we found was that there was no one application component that dominated all metrics, right? So rendering and VIO took a lot of time, but asynchronous reprojection, which took a very short time, was really important to motion to photon latency. And so if I just focus, if I gave all my resources and prioritize VIO, this poor reprojection is not happening on time, and my quality really suffers. Okay, so I need to consider all the application components in the system together. Power consumption, I think this community is probably won't find this surprising, goes beyond the CPU, GPU, and DDR. We need to think about the system level components, the sensors, the display, and the IO. There's a significant variability in these workloads. So, depending on the scene around me, depending on what is being displayed, there's a lot of variability in the computation time and the power consumed. And so we need to be careful to partition and allocate and schedule our system resources. And finally, per component metrics do not capture QoE. So you can't just look at VIO and say, and you'll see some proof of this later, and say, hey, my pose is good, and so my system is great. Can't do that. We have to look at the entire system to make the end-to-end QoE-driven trade-offs. Okay. The next set of results and implications come from looking at each component separately. The previous slide was about the entire system. So we looked at standalone components and did a lot of profiling analysis of, how many instructions per cycle, memory usage, et cetera, where is the time going within an individual component, and so on. And what we found was, even within a component, right, there are many tasks, high-level granular tasks. And across all of the components, I mean, again, there was like no single task dominance. There's just no silver bullet here, okay? So you need automated techniques. So if you're going to decide, because power, right, today hardware people, we look at power as a problem. First thing that pops to mind is let's build an accelerator, okay? But there's so many tasks here. What are you going to accelerate? We need techniques to figure that out. It's impractical to build an accelerator for every single task, so we need to build shared hardware. How do you do that? There's a huge diversity of compute and memory primitives. How do you build flexible memory hierarchies? Algorithms are in flux, so you build an accelerator today, 6 months later, you have a new algorithm, right? And your accelerator is out of date. So how do you design things in a programmable, extensible way? And then different algorithms have different trade-offs, different quality of experience versus resource usage profile. How do you do this end-to-end QoE-driven approximation so that you can get the whole system together? All right, so Elixir really provides us with a rich playground to do this type of research, to think about designing systems with these implications. So that's what I'm going to talk about next. In the little time that I have, I'm going to talk about some key research. There's lots of research being done with Elixir, not just by us, by others as well. Today, I'm going to highlight 4 different sort of sub-projects because each of these comes from a different implication of the result of the findings that I just talked about, and exploits a different aspect of this end-to-end system design. The first one is hardware acceleration. I'm a hardware person, so that's well, these days I'm an every person, but I come from the hardware community, let's put it that way, and so that's closest to my heart, so I'll talk about that. Then I'll talk about device edge cloud co-design. Then I'll talk about co-design approximation, and then quality aware execution frequencies or frames per second. So let's see how much I get through. So hardware acceleration. I mentioned earlier, we identified many high-level tasks for the basic XR configuration. We identified 27 of these, fairly high-level granular tasks. And so the first thing that pops to mind is, oh, let's build an accelerator for audio playback. Let's build an accelerator for VIO. Let's build an accelerator for 3D reconstruction, right? And each one is a different paper. Maybe you get 4 papers because you build different accelerators for each of these. But really, is that the right way to build a system? Okay, should we be building these monolithic accelerators per task? Well, what's the other option? The other option is, and yes, you can't see this because there's just too much. What that text is about is for each of these granular tasks, we found out what are the key primitives that these tasks uses. Okay, so can we identify, and we did all of this manually right now. So the question is, can we identify a set of common finer grained primitives, okay, that are used across the board, and then build these fine grained accelerators and then compose them on demand, right, to do the higher level tasks that you want to do. So which is it, right? Should we do monolithic versus composable fine grained accelerators? Okay, so there's many different taxes that you have to pay when you want to accelerate something, when you want to accelerate hardware. And the monolithic and composable fine grain have trade-offs. So with monolithic, the design cost is high because every time you want to do some new task, you want to think about the accelerator for that. Versus with composable fine grain, hopefully you have the key primitives and you're just composing them. Utilization for monolithic is low because again, you have very specialized hardware that you use only when that task is going on. Area leakage power, same reasons. It's worse for monolithic than for composable fine grain. But the problem with the composable fine grain is what we call the control tax, which is that every time you invoke a fine grain, every time you invoke an accelerator, typically you're going through the OS and you're paying a big tax, right? And if you're doing this on a fine grain basis, that's too high a tax. Same thing for data movement. You move data between the CPU and the accelerator, and you're paying that tax every time that you invoke a fine grain accelerator. So what we tried to solve in our work was to get rid of that control and data movement tax and get the best of both worlds. So very briefly, here's a case study that we did with our collaborators from Columbia, Luca Carloni's group. So this is using the 3D spatial audio that I talked about. This is an off-the-shelf open source library. It's about 6,500 lines of code. So it's, fairly high, lots of code, right? And so what does it have? It has something called a psychoacoustic filter, which you'll recognize, FFT, FIR. I mean, this community has been doing this stuff since ages, right? There's a bunch of rotate order stuff, a zoomer process, and a binauralizer, which again has FFTs, FIR, and so on, okay? And if you do profiling, about 80% of the time is spent on FFT. And then the next thing is FIR, okay? So let's accelerate FFT, right? We know how to do this. In fact, Luca's group already had an FFT accelerator. We use the Columbia ESP infrastructure, very wonderful infrastructure. Let me put a big plug for it, for doing heterogeneous shared memory SoC. So it lets you instantiate an entire heterogeneous shared memory SoC easily. We added a bunch of support for cache coherence and so on to do efficient shared memory with it. Okay. So we accelerated FFT and the speed up was 1.5, right? Not great, okay? Why? Because again, we're doing this fine grain acceleration, huge control and data movement taxes. Plus, remember there was this little FIR between the two FFTs. So you're going back and forth between FFT and FIR. FFT is fixed point, FIR is floating point, blah, 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 paying too much overhead. Okay, so you say, all right, let's accelerate FIR then. Okay, so now the question becomes, do you do this monolithic acceleration with that whole chain FFT, FIR, IFFT, or do you just do a fine grain acceleration where you're doing FIR separately, FFT separately? Hopefully you have all these IPs already and you're just putting them together in this nice heterogeneous SoC. Okay, so the blue bar is the monolithic accelerator, and the speed up went from 1.5 to 3.1, good. The composable fine grain, where we had a separate FFT, separate FIR, all in a NOC, right? Communicating via shared memory. Speed up increased a little bit, but it's 1.8, okay? Not not at all competitive with monolithic. Okay, so I don't have the time to go through the actual techniques we used, but we came up with a new technique to bypass the OS entirely every time we do this fine grain accelerator invocation. And we do this instead through an efficient shared memory approach. We also modified our coherence protocol using ideas we've been building on for a long time called the spandex cache coherence, which very efficiently allows you to move data from a producer to a consumer while maintaining the shared memory abstraction. And so this enables us to chain accelerators, to pipeline accelerators, and essentially treat accelerators as first-class objects. And with that, our speed up jumped. Not only did it jump to 6x, but the key thing is that the gap between composable fine grain and monolithic coarse grain is now, it's very, very competitive. Okay, so now we have the foundation to think about using these composable accelerator techniques for thinking about an entire XR SoC. So we already identified various primitives. So now, what are the primitives that we want to support? And then we compose them on demand, right, at runtime as the application executes. Now, of course, ideally, we want to automate this process of finding the primitives, figuring out what to accelerate, et cetera. We made a first pass of this in a paper that was accepted, that recently appeared in ACM Text. This is joint work with Vikram Adve, David Brooks and Guyan Wei from Harvard, and Sasha Misailovich from Illinois. And here we use a novel compiler IR to represent heterogeneous parallelism, which is work that Vikram has been leading for a while, and use that to do this automation. Okay, so that's the work on hardware acceleration. The next idea that I want to talk about is, and I'll just spend a couple minutes and then conclude very quickly. It's about device edge cloud co-design, and in particular offloading. So acceleration is great, but as I said, algorithms are still in flux, right? And so even though VIO is one of the top consumers of power, doing hardware acceleration gives you huge benefits, but then the next incarnation rolls around of a new algorithm, you can't take advantage of that. And so we said, can we save power by offloading VIO, moving it to a remote server to the cloud instead, for example? And the key challenge there is network latency, because there's many time-critical parts of XR, as I said, and the head pose is something that's used a lot. So we can't take that entire network latency time. And the key insight there was to offload the accurate VIO pose part to the cloud, but keep the IMU part, which is the inaccurate but fast and more efficient part, on the device, and use the combination for an end-to-end system. And the surprise we found was that offloading works well for normal conditions, right? Regardless of the network, Wi-Fi, 4G, 5G, we did all of that. But the standard metric for pose evaluation, which is the average trajectory error, it does not always predict end-to-end user experience. So, the ATE could be that, offloading is just fine. But if you actually see the experience through the headset, you see differences. And so what this showed us, again, was really the importance of doing end-to-end systems work, doing the user studies, and it also showed us that we need more XR-specific data sets and applications, because a lot of the VIO-related work really comes from the robotics community, and not really, there's very little by way of XR-specific work. So I don't have the time to go through any more details of this, but we've, and again, this is part of today's release. We have built a client server model on top of Elixir. So now you can offload things to the cloud using TCP in this case. And I'll just show you a video. We got about 20% power savings for the full complete end-to-end system, 47% for CPU, but the quality of experience was really the interesting one. So this is my student. You can see her in the corner there, walking around in the lab in the physical space. And this is she's going through a Zen garden. This is running on the Unreal game engine. And you can see, and the VIO is happening on an Amazon instance. It's fine, right? With the remote VIO, tracking is great, rendering is great. And later on in the video, she actually does some jerky movements. Things still work great. This is a flight simulator that a student wrote, again on Unreal, and this works great. Again, VIO is offloaded to Amazon's servers. But the interesting part was, he said, okay, so that was like in the lab, right? We're running the network in the lab, not much latency. What if we injected latency to look at normal conditions? That's the ATE graph at the top, and you won't really see anything unusual in the ATE graph. You look at it, you say, offloading is just fine. The x-axis is the different latencies. Deal seems to work reasonably well at different latencies, or at least I can't tell which latency things are going to go bad. But look at this video here. The left side is with no added latency, and the right side is with 400 millisecond latency. And you will see, like you saw that steering wheel, it jerked like that. Right? You don't get that type of thing looking at ATE. You can get it only when you look at the real experience. And we found that you really need to do these user studies. It's a different way of doing things. And so we're looking at various other offloading techniques. The next thing I really wanted to quickly talk about is co-designed approximation. Again, the point I'm trying to push here is this whole idea of co-design and the idea of looking at end-to-end and the idea of building real systems. And in this one, we looked at foveated rendering, which is a rendering technique that makes rendering be energy efficient. Today, rendering is very expensive due to various reasons. With foveated rendering, you figure out where the user is looking, and you only do high resolution for that part. Okay, so for the rest of it, you're not really, you can do lower resolution, which means cheaper, less expensive rendering. The problem with this is that you need to track the eye, right? And so you typically, this is done through neural networks. That takes energy. And typically the neural network energy outdoes the savings that you get from foveated rendering. All right, especially because you want to do this with strict motion to photon latency. And so the commercial systems that do foveated rendering, what they do is they do fixed foveation, meaning they say, I'm going to assume the user is only looking at the center, okay? And the center is a very large fovea radius. So they don't have overheads of gaze tracking, but they have higher rendering energy because you have a higher fovea radius and suboptimal quality, because if you looked at other parts of the image, you're not seeing the right, a good quality. And so there's this trade-off. And what we showed was that if we did end-to-end, if we looked at the gaze tracking, we looked at the rendering, you worked on them together, and I don't have the time to go through all of this, you can save a huge amount of energy without affecting quality. And again, we did that by actually seeing the system. Okay, so for the first time, we showed tracked foveation is more efficient than fixed foveation. And then I have a bunch of other, one other technique with quality-aware frames per second scene reconstruction, but I'm going to skip that in the interest of time. There's tons of work being done with Elixir by us, by others. Again, I invite you to look at it. Just to conclude, we are in at the brink of a new immersive era. It's going to transform how we design, program, and use computers. We really need a new style of research that's human perception driven, full system, enables new applications. We need to build systems, chips, compilers, runtimes, applications. I encourage you to do all of that and use user studies to evaluate the system goodness. So we are trying to do this through Immerse and through Elixir, and I encourage you to join us. Elixir is a community, so there's various ways of participating.
Well, let's thank Professor Edwin for that wonderful talk. I know we are a little bit short of time.
Yeah.
I do have one question on the online, actually.
Okay.
While people, we'll take a couple questions if people are okay.
Yeah.
So the question online is, I forgot the name of the person, someone from NTU. He's asking, wearing all these, gadgets and stuff, does it have any side effect on eyes and brain?
Yeah. So that is why, great question, right? So that's why we have that whole human experience thrust in Elixir, because we want to work on these things. So working with psychologists and neuroscientists and so on to understand what are the impacts, and as system designers, what can we do to reduce those impacts? And some of the, so definitely the answer is yes. These are hard problems and we are making efforts to solve them. Yeah.
I hope we will have an impact on reducing that side effect.
Yes, exactly.
One more question. Ed.
Thank you, Sarita. Wonderful talk. I have a related question, which is inspired by the fact that this is our first in-person meeting since 2019.
Yeah.
And I recently read this book by the philosopher David Chalmers, who just published this book called Reality Plus, where he argues that there's no fundamental difference between virtual reality and physical reality. And I was wondering if you worry about the societal consequences if you're wildly successful.
Yeah, no, this is a really good point, which is why, again, this is why I established Immerse, is because we don't want to lose that fact, right? We don't want to lose sight of the societal consequences. I mean, my kids are now in college, but I went through the teenage years when, they're like, even with the mobile phones, their heads are always down, right? And we don't want that to be happening, and this can do even worse. I don't have answers for you today, Ed, but all I will say is this is really, really high on my mind, and that's why we brought all of these people together for Immerse. And hopefully in another few years, I'll have something far more intelligent to say.
Last question. I saw your hands up, so.
Thank you. Again, thanks for that glimpse into the future. Actually, my question is somewhat similar along the lines of Edward's. Namely, over the last couple of years, we had this huge user study on how we can virtualize things, including full conferences. So I'm wondering, had that some impact also on your line of work? Did you see some things differently now, for example, than
you mean like because of COVID?
Right.
Yeah. Oh, it was horrible. So I gave a keynote at ISCA last year, which was the first time that ISCA happened, and I started off showing a picture of, pre-COVID times with all of my students, right? Looking at, interacting. It was a very sort of interactive picture saying, look, 3D immersive, amazing experience. And the next slide was flat Zoom screen. And look, what is this? So COVID has only shown us how bad things can be, right? If we don't do the virtual stuff right. And so I think a lot of, there have been advances in terms of conferencing that are more interactive than just flat Zoom screens, but we still need a long way to go. In fact, I had like 5 minutes of my ISCA talk was about what we, impact of badly done VR.
Thank you.
Are you trying to give me a hard time? Last question, right? Last, dead last.
No, my apologies. I ran over. Yeah.
In your research, how far do you think? I think Matrix would be the next version of metaverse, right? As in where you have a full experience rather than just a visual experience. How far do you think these technologies are that I don't have to go to the beach and it would be like almost perfect?
I don't have
virtually.
to go to one?
Go to the beach and it would be almost perfect.
So you're all asking me very similar questions, right? And we are very good. I mean, we are much better than we used to be, but literally I keep saying the word orders of magnitude away in terms of power, performance, and quality of experience, right? But the thing about what I really enjoy working with these technologies is that I don't have to be all the way realistic to get the benefit of these technologies, right? I can define mileposts, right? And so that's actually one of the things we're trying to do with Immerse is to try and define like Moore's law kind of mileposts for progress and measuring progress, right? You don't have to really be on the beach and enjoy completely realistic every single thing, like feel the breeze on you and all to actually exploit these technologies, okay? We're not there yet. Going back to the question he was asking, right? So even like what you really want for these conferencing things is actual realistic holograms. There's been a lot of progress, but very hard still to get that realism in, even having like dealing with people, right? Holograms of people is still very, very hard. So yeah, but we continue to make progress and there are clear mileposts that we can hope to achieve. So I think this technology is at a point where we should work on it now.
Well, let's thank Professor Sridhar one more time for that wonderful talk. That was really great.
Thank you.
And as a small token of appreciation, we made this special photo. I think it's a representative of what is special about Hamburg.
Oh, nice.
And that was your.
It's beautiful. Thank you so much.
Yeah.
All right.
You can take a picture here.
Yeah.
Thank you very much. Okay, so 10:30. Well, for now, coffee time. 10:30. Go to the different presentations.
Also have certificates.
I forgot that part. We'll just give it to her. I think that one is more interesting.
Yeah.
That's a certificate. Yeah.